In this mini lesson, we will try to increase our understanding of squares and square roots. Squaring a number and taking the square root of a number can be considered inverse operations, similar to the relationship between addition and subtraction or multiplication and division. One operation undoes the other. Let's examine this idea more closely. To square a number means to multiply it by itself. For example, if we want to square the number 6, we would multiply it by itself, and our product is 36. So we think of 36 as the square of 6. Another way to write 6 squared is to write it as a power. 6 to the second power, which we also read as 6 squared, would mean to take the base 6, multiply it by itself, use it as a factor twice, in other words, since the exponent is 2, again resulting in a product of 36. Inversely, taking the square root of a number means that if we start with 36, we are asking which number, when multiplied by itself, would give us 36. And that number is 6. This, by the way, is the symbol for taking a square root. It's also sometimes called a radical. So we can do this similarly with other integers. We could take, for example, 4 and square it. So we could write it as 4 times 4, or 4 squared, which would be 16. And the inverse operation would be to take the square root of 16 and get 4. Let's explore these concepts a little bit further. If you look at the square, let's give it a length of 6 inches on each side. So if we find the area of that square, we would multiply its base times its height, which in all squares is going to be the same. So we're basically saying take the length of the side and square it. In this case, we get an area of 36 square inches. And so therefore, when we're looking at the square root, the number underneath the square root symbol, which can also be called the radicand, is the area of a square, and so its square root will be the length of its side, which in this case is 6. Now so far we have limited ourselves to talking about perfect squares. What exactly are perfect squares? Well, these are simply the areas of squares whose side lengths are integers. So, for example, 1 is a perfect square because 1 is equal to 1 times 1. It's the area, it represents the area of a square whose side is length 1. 4 is a perfect square whose side lengths are 2. And we can continue to find perfect squares by just continuing to use the integers and multiplying each integer by itself. 3 times 3 is 9, 4 times 4 is 16, and so on and so forth. Now every integer has a square root, but most numbers are not perfect squares, and so therefore their square roots are not integers. Take, for example, the square root of 12. So we know that 12 has a square root because there is a square that can be created with area of 12, but its sides will not be a whole number integer. So it's not considered a perfect square. We can approximate it, however, by looking at the perfect squares on either side of 12. 9 and 16 are the two numbers that are perfect squares that 12 lies in between. And since the square root of 9 is 3, and the square root of 16 is 4, we can conclude that the square root of 12 must lie somewhere between the integer 3 and the integer 4. An important characteristic of the square root of numbers who are not perfect squares is that they fall into the category of irrational numbers. That is, they cannot be expressed as fractions, and as decimals they are non-repeating and non-terminating. The square root of 12, calculated to the first 9 decimal places, as you can see, none of the digits repeat. And if we were going to punch this into a computer that could approximate to many more decimal places, it would never end and the digits would never repeat. That is considered an irrational number. The set of real numbers consists of all irrational numbers, such as these non-perfect squares, and the set of rational numbers, which are those that can be expressed as fractions. More to come. Thanks for listening.